Welcome back, class. Um, Before we do problems related to these advanced MOS topics, I still have to finish a couple of slides, a few slides on the theory because we ran out of time in my last recording, the theory recording. So we were at this slide where I introduced you to the basic principle behind dynamic MOS, right? Um, this topic is dynamic MOS logic circuits 14.3, and I said that the big advantage is that you can get rid of the PUN, which means half the gates are gone, but you do have to introduce two new transistors, one a NMOS and one a PMOS, to make this dynamic MOS work. So you gain some advantage, but you also have to sacrifice a little bit. So the principle of how this MOS operates is also something I talked about. I told you that a clock is required, and as the clock does its periods on and off, we divide the action into the pre-charge phase and the evaluation phase. In the pre-charge phase, all that happens is QP, the PMOS transistor, turns on because phi, the clock is 0, and so VDD comes to charge up the capacitance at the load CL. So this goes high and it stays high at the end of the pre-charge. In the evaluate, basically evaluate means you check something, right? So in the evaluate phase, you check to see what the logic is asking in the PDN. Is it asking for the output to go high? To stay high, or is it asking for the output to go low? If it is required that it stay high, then you don't have to do anything. Just keep this open and nothing happens. But if it's asking for the output to fall back to low, then a path is created here. This turns on because phi is low. Sorry, phi is high. That's why Qn, this is an NMOS, so it turns on. And the charge here is drained so that Y becomes low. So that's the logic, and we have some examples that we'll come back and do later. But one thing to understand is that this dynamic MOS process also has a number of problems, and here are the issues. Noise margins are rather low. Noise margin high is okay, noise margin low is definitely low, NML. Output voltage decay due to leakage effect. So we think that the charge on the output capacitor CL just stays there, but it doesn't. It starts to decay, and so the output voltage which you are supposed to hold at VDD starts to decay also. So that's another problem. Charge sharing. This is because there's not only CL capacitance, there's also other capacitances through which the charge can leak out. So that's a problem too. Lastly, when you try to connect the output of your this dynamic MOS gate to another similar gate, so the output of one inverter or logic gate becomes the input of the next, then that process is called cascading. You're connecting two in cascade. But even there is a problem, and that's a serious problem. So it doesn't affect the first gate so much as the second gate. The second gate, unfortunately, cannot hold its output voltage again at the necessary high value. During the process, it starts to leak. And that's because the output capacitor of the second gate starts to prematurely discharge while it's not supposed to be discharging. So that's a problem. And to overcome that, to overcome this, we're not talking about how to overcome the top three, but to overcome the bottom problem, the cascading problem, they've come up with a new form of the same system, but this is called domino CMOS logic gate. Okay, so it's the same dynamic MOS gate without the PUN and these two extra transistors, but now you put an inverter stage in the middle before X and Y. So to solve the problem, obviously you have to put more hardware. So again, your cost goes up. But basically, and this is just a static inverter. It's a CMOS inverter, consists of both a NMOS and a PMOS device, but basic inverter. Whatever is the input, the output is reverse, right? So with that, we find that the problem of premature capacitor discharge, which actually happens here, this discharge damages the output. Without this I1 and I2, the inverters, this capacitor tends to lose charge and this output X2 falls when it shouldn't be falling. But because of these two inverters, they provide a strong level between this stage and this stage, and that ensures that there is no fall. It has a name domino because the outputs Y1 and Y2, they come one after the other. It's like a dominoes falling, right? You can see the shape here. So that's why it's called domino CMOS logic. So this is one technique to fix a problem with the dynamic MOS. I won't go too much into this. We're not going to look at any problems, etc. But if you ever run into domino CMOS in your life, you can come back and look at this material and begin to understand what this is all about. Okay. All right. Now I will go back to our problems for all of the material that we covered so far. Okay. So, well, we're back at the beginning. I keep scrolling past these slides. Bear with me. Okay, I'm on slide 15, where we are at our first numerical problem. So this is an exercise. So an exercise is in the pages of the lesson, not at the back. And here all we have to do is find VOH. So we are given some details about an NMOS transistor switch. That's all it is. We are given the VT, sigma, phi, VDD, find VOH. Now VOH is a simple formula, VDD minus VT. This is the body effect formula to find VT, which is not a constant, right? And so let me show you how I solve this. So all this data is given on this side. Vt, this formula for VOH, use VDD minus Vt. So Vt can be written in this form, but this VOH is again VDD minus Vt. So you get an equation with Vt on both sides, and there's a root here, square root. So basically the headache here is that you get a quadratic equation in Vt square. So you can follow the steps, they're simple steps. So you get an equation in a square. If you solve that, you get two values for Vt. One of them can be ignored if it's a negative value. The other is the value you take. Then VOH is VDD minus Vt, which is 1.15 volts. Okay. So make sure you understand this process. I wanted to do this because of this very fact. This is a bit of a complicated thing. So you have to go step by step to solve it, come up with the square equation in Vt square, solve it using a quadratic equation solver. I found a program online where you can just plug in the coefficients and you get the values of the roots, and then you can solve for VOH. Okay? All right. Get some practice because this could be an important step in solving bigger problems in the future. Next we come to example 14.2 in the textbook. Now this is quite a complex problem. In fact, we will do one problem and this is just for an NMOS transistor switch. We have an identical problem for a CMOS transmission switch. Both I will do with you here, and you have to pay attention because it's a long problem with lots of little things tucked in. More importantly, as we solve this problem, we actually will better understand what exactly is happening at the NMOS switch and later on at the CMOS transmission switch. Because the transistor here, it's a single transistor, right? An NMOS switch is just one transistor. But with a complementary CMOS, you'll have two transistors and they'll keep switching the drain and source. They'll go from saturation to triode. So all those little things that happen, you can follow through this, working out this example. That's what I meant to say. Okay, so please open your textbooks to example 14.2, and I forgot to put the page number, but you can find it and follow along with me. Okay. Also, you'll have to read the example a couple times yourself so that you totally understand it. For now, I'll try to highlight the big items, big issues that the problem handles. Okay. So in the problem statement, you have to it talks about both circuits, 14.8 and 14.9, which refer to 14.8 is this single NMOS switch when the input is going high, and 14.9 is when the input is going low. So when the input is going high, we know the output goes high because this enable is always connected to VDD. Similarly, when the input is going low, the output also falls. So that's the basic idea, and you have to do both. Also, remember, we are interested in this TPLH point. This is as the output starts to rise, at what point does it reach half its output value? Similarly, as it falls, we are interested in the point at which it falls to half the original value, right? So both these are of importance, and that's what the question asks. So given a lot of information and the fact also that the capacitance between the output node and the ground is 50 femtofarads. So with all this information, we got 1, 2, 3, 4, 5 things to find. First of all, for the case with Vi high, that means the input high, find the V output high, right? That's one thing. Then he is given the fact that the output of our switch is going into a CMOS inverter, right, which has both a NMOS and a PMOS device. In that inverter, he wants us to find the static current in the inverter and its power dissipation when its input is as found here. So VOH is found. If that VOH is the input to this inverter, then what is the static current of the inverter and its power consumption? Also, for that inverter, find its output voltage. So this is kind of not so much about the switch, but the next stage, which is the inverter it's feeding. Then we come back to this switch, find TPLH, which is, the low to high when it's going high. Then for the next case where the input is low, find TP high to low. Based on both these TPs, find the average propagation delay TP. Okay. So here are a bunch of formulas that I thought I'll give it to you right away. Okay. Now let's work backwards. Item 5 says find TP, right? You know TP is the average of TPL high and TP low to high and high to low. How do you find low to high? You have to take the capacitance, multiply by VDD by 2 and divide by this ID, which is the average current when the output is going from low to high, right? That's low to high. Similarly, high to low, same formula, but the denominator current, the average current, is now what is happening on the high to low portion, right? Uh, so, so you have to find the two denominators. Now, to find the two denominators, you have to use this formula, right? Uh, to find, you need two currents here. One, when the diode, when the device, the drain current is at t equals 0. Another current you have to find is in the drain circuit when time is not t equals 0, but the time is at the point when you've reached the TPLH point, when you're halfway up or halfway down. So you use this ID twice, and one time it's in uh, saturation, another time it's in triode. So you apply both formulas where, yeah, here it never goes to triode, so you don't apply that formula. But when we do CMOS complementary, you'll find that you have to do both triode, both saturation and triode formulas. But here you'll just use this one formula. But to be able to use VT, you got to use this formula. So all these steps, one after the other, have to be done, and that's what is done in the exercise. Okay, so I'll quickly go over A, B, C, D, E, and then you can follow this and read it also by yourself, please. So first of all, to find VOH, right? The same method I just showed you, a quadratic equation first has to be written, and then you solve to find Vt. The quadratic equation is in square of Vt. Then you'll find Vt to be 1.6, and then from there you can find VOH is 5 minus 1.6, 3.4, right? So when you are expecting VDD 5 volts, you're only getting 3.4. So that's quite a loss of signal. Part B is all about the inverter, and there he uses the formula for saturation current or current in the saturated PMOS device. This VDD minus V0 is actually V gate to source voltage. So if you use this formula, you can find ID for the PMOS. And then he also does power, static power as 90 microwatts. That's a simple P equals VI. Okay. And also he finds the output voltage quickly. So that is part B, and I'll let you read it. Part C, to find the point time where PLH actually happens. That means where the output voltage reaches half of the VDD, right? So to do that, like I told you, you have to use these formulas, right? To do this formula, you have to find these two currents, take the average. So he walks you through that step one by one. The two IDs are found first. Then the ID average is found as 425 microamps. Then the time at which this 425 microamps happens is found using that final formula, this formula, to be 0.29 nanoseconds. Then he goes to part D. This is where the output is falling. Now you have to find T for P high to low, which using the same methodology, finding the two currents, finding the average current, then using this TPHL formula, he comes out with TPHL to be 0.17 nanoseconds. Then the total propagation delay is this, and it's 23 nanoseconds. Okay? All right, so complicated formula, but you go through this, you learn a lot about what exactly is happening in the various points in the MOS switch. All right, I'm going to move on to exercise 14.4. Give me a second, I'll be back. So this exercise also is in the textbook. In fact, the answers are also given. And it is a CMOS gate this time, or CMOS switch. So the basic information about the devices, it's actually, this is all a repeat of what we saw in the previous example, right? Same data. So that kind of makes it a little bit easy, and he says, use the information or the results you found in the previous exercise as much as you need. So it helps us save a couple of steps, not a whole lot. Basically then we still have A, B, C, D. We don't have that one point in the previous example where we had to find some currents of the second next stage, the inverter stage. Here luckily we only have to worry about this portion when the output is going high, and this portion when the output is going low, and not worry so much about the next CMOS inverter stage. Okay. All right. So here the one thing that has changed is that the output capacitance is now 70 instead of 50, which was previously the case, and that happens because now we got a PMOS device that adds a little bit of capacitance also. All right. So given this data and this switch, what are the four parts? First, find VOH and output high and output low, right? So that's the first thing. Output low we know is going to be 0. Output high, because it's a CMOS, and they tell us that once you have a CMOS, you go back to being at VDD. So the answer is easy. VOH is VDD, VOL is 0, right? It's a perfect switch. B, C, D are similar to what we did previously for the MOS only and MOS only. You have to find the currents, both the NMOS current and the PMOS current, at 0 time and at time PLH, which is low to high. And then you find this is the current at that point, and you actually find at what time does that TPLH point happen. Then part C says for the falling, that means the output going down when input is 0. Same thing, find the currents at time 0 and at these times. Also, at what value of VO will QP turn off? That's one extra question, right? QP turns off. At what value of the output will it go away from being in saturation to entering triode or cutoff? Last thing, TP, which is the average of the TPLH and the TPHL. So that is the problem. Let me open up my notes. Exercise 14.4. Okay. So for any transmission, CMOS transmission gate, VO high is VDD is 5, VO low is 0. Okay. Next, we got to find all these currents. IDN at time equals 0, this formula. IDP at time equals 0, this formula. At 0, we know that we can just use this VT, right? You don't have to solve and find VT specifically. Capacitor current, or the charging current as they call it, is the sum of these two, which is 1120. From exercise 14.2, from example what we just saw, there we had only one device, we call that was an NMOS device, and we found the current at this TPLH to be 50, right? So we are borrowing that value from there because the switch is the same, the process is the same, and the TPLH happens at the same time. But we still have to find IDP because previously there was no PMOS, right? There was only one device. Now we have both. And to find this, we use the triode region formula. Why? Because the QP, the PMOS transistor, it will enter the triode region as soon as VO reaches VTP, right? So once VO, the output, is slightly higher than VTP, which is, isn't it 1 volt? VTP, yeah, is 1 volt. So at that point, it's not in saturation anymore, and it enters the triode region. And so you now have to use the triode region formula. So once you use that formula, you get 275. Now, to find TPLH, right, the time, you use this formula. But to use this formula, you need the average current. The average current is the sum of the two currents. This IC0 we already found as 1120, but this IC-TPH is again the sum of the NMOS and the PMOS currents, the 50 and 275 which we have here, this 50, this 275. So if you add those, you come up with 325. Then the IC average is 1120 plus 325 by 2, which is this formula. That's 722. If you plug that in, then you get the exact time at which the P low to high point happens, the P low to high, from this formula. Here's the capacitance multiplied by VDD by 2 by the average current, and that happens at 0.24 nanoseconds. Okay? All right. Part C is about high to low, right? Part C says we are talking about this figure where the input has now gone low or 0, and the output has to then fall down, right? So to do that, most of the same formulas we use. First we find current at 0, which is really the same. Current in the PMOS at 0, also which we found already. The total current is the sum of the two. This is previous work. The new work now is to find the new IDN at P high to low, right? So that happens when the triode, when N is in triode region now. The NMOS device moves into triode, so you use this formula, okay? So this gives you 688 microamps. To find dP, the current in the drain of the PMOS at this TPHL, we must first find TP when V0 equals VDD by 2, right? Because VTP has this formula, so plug in the fact that V output at the half point uses this formula, and you end up with a value for VTP as 1.49. Okay? So then you can find dP at this time, at the exact point where your TPHL happens. This is just the saturation formula, and you get 20 microamps. So to find TPHL, you use this formula including the capacitance. Again, you need the denominator, the average, which is this. And to find this, you sum up the two previous currents, average divided by 2, 914, and then you find this is 0.9 nanoseconds. Okay? So there was another part here for C. At what value of the output will QP turn off? Now remember, the output is falling, right? It has to fall down to 0. So on its decreasing slide, when will this QP stop conducting? That is the question. So QP will turn off when V0 equals VTP. We know this, right? So that means you need to find a specific VTP, again with VDD. All the rest of it is given, and so you come up with VTP as, unfortunately, another square function, right? Because of the square property here. So you have to do the squaring, solving the quadratic equation. You get a positive value and a negative value, and finally you get a value for VTP as 1.61 volts. So QP will turn off, the PMOS switch will turn off when V output equals this VTP, which is 1.61 volts. Okay. Last point is, when will TP, what is TP? The total transmission propagation delay, that is 0.22 nanoseconds. Okay. So we did two of these problems, one for the NMOS switch and one for the CMOS transmission switch. Please go through this in detail, read the notes accompanying the theory also, because there's a lot of things happening with the two devices. They go from saturation to triode to cutoff and all that. So make sure you understand the logic on the theory and how the problem itself, the two problems, are being solved. I'll be back in a second. Okay, now that we have finished with these two complex problems, the remaining few, most of them will seem simpler, more easier, but there's also one that may take a little more time, one example. So, but luckily that's an example, so you can spend more time on it by yourself. All right, so I'm moving ahead to slide 27, where I have a problem from the back of the chapter. So here there is a transmission gate. Some data is given, W by L, etc. And C, the output capacitance, is given as 10. Here we have to find an estimate of the transmission gate resistance and then find the propagation delay. You have to do this for both step and ramp inputs. Okay, so this is problem 1422. It's pretty straightforward. We are going to use the empirical formula, this formula. So from there you get RTG. If the input is a step function, you use this formula to find TPLH. If the input is a ramp function, you use this formula, no 0.69, just CR, and you get the 2. So pretty simple, not worth wasting too much effort on it, but make sure you understand what ideas were used there. Here's another exercise from our textbook, and here also we have a transmission gate, and there is an inverter on this side and an inverter on that side, right? We've seen this in the theory. This can be converted to a simple RC network like this, and then we can apply some formulas to find the estimate of the propagation delay TP as this. So it's a straightforward application of certain numbers, and I can show you how that is done quickly. Exercise 14.7. So use the empirical formulas for RP1, which is the resistance of the first inverter, the PMOS device. Then the transmission gate resistance, use this formula. TP, just plug in the numbers and you get TP. Okay, so this one. Remember that R1 is actually replaced by RP1. Okay, all right, so I don't want to spend too much time on that. Yeah, we've got an interesting problem here, exercise 14.8. Here, remember, this was one of the types of logic circuits that we said, we showed you 3. There's a realization of a 2-to-1 multiplexer using pass transistor logic, realization of the XOR function, and there's something called complementary pass transistor logic, or CPL, where you use these gates to come up not only with an AND but also a NAND. Okay, so here's an example exercise related to that. So what he's doing is he's taken this figure which he showed us previously, this figure for AND and NAND, and he's switching things. So what he says is B and B bar are switched. So B bar now applies to pin 5, and B goes to pin 6. So if that happens, he asks us to find the output. what is the output, right? And what we find is, we find that the output becomes A or B. Instead of A and B, it becomes A or B, the output here, and then the output for the complement becomes the OR becomes NOR, or both OR and NOR are available. OR is available there, NOR is available here. Then he makes another change. Here the terminals 5 and 6 are interchanged as in A, that same thing applies, and the signals at 2 and 4 are changed also. So 2 and 4, they also become A's. In fact, they become A complements. So with that, then what happens to the outputs? And the answer is that you get a exclusive OR, and here you get a opposite of an exclusive OR, which is the exclusive NOR. Okay, so that's interesting how that needs to be solved, and I've shown how that's done here. You actually also end up having to use this little table of Boolean algebra rules. So for example, here, if this is B and B bar now as switched, then Y becomes, on this path you have AB bar, on the lower path you have B and B. B and B is just B, and then AB bar plus B is nothing but A plus B, which is an OR function. Similarly, you can see that the bottom then becomes a straight NOR function. It ends up with this, B and B bar becomes 0, right? Like A and A bar here is 0. So this goes away. So it's just A bar B bar, which is complement of A plus B, or A. So it makes it a NOR function. All right, I'll let you look at the rest also. It's not too difficult, but it helps us go back to some real logic, which we almost have forgotten. That's why we are studying all this stuff, right? All right, I have one example which is in your textbook, 14.3, which again is a little bit like some of the earlier stuff we did. It's a little tricky. So this is a dynamic MOS NAND gate, right? So we only have the PDN, which consists of A, B, C, D, all 4 of them in a AND configuration. We don't have anything on the top because the PUN goes away, but we have this transistor QP and this transistor QE with the clock in their inputs, right? So this, we have seen the logic, the theory. What we have to find here is, given all this data, consider the pre-charge operation. Remember, there's a pre-charge operation and an evaluation operation. In the pre-charge operation, with the gate at 0 volts, that means the clock is at a low, CL is, and assume that T equals 0, CL is fully discharged. Now this CL will charge, right? During the pre-charge operation, the capacitance will charge up to the Y will be equal to VDD. So find the rise time. That means how much time will it take for the output to go from 10% of the final VDD to 90%. So that range 10 to 90, what is the time to for the rise is what needs to be found. Part B says if A equals B equals C equals D is in 1, that means all these have a 1 at their input, a high at their input. Then what happens? This PDN is now on because it's an AND function and all are 1, so it's on. And so whatever was at Y, whatever the voltage was at CL, the charge has to discharge through this last transistor NPN when phi is high, when the clock is high. So in that process of dropping from high to low, find this TP high to low point, which is where it drops to half of the VDD. So these two things have to be found, and luckily for you, it's a solved problem. So you can work through the steps one at a time. I think the explanation is pretty good. To do part A, you have to use the same formulas for finding, t t time. The time can be determined as the change in the voltage times the capacitance divided by the average current. We've seen that formula before. But to do that, you now have to find the average currents. So you have to find the current when the output voltage is 0.10% of VDD. At that point, the device, this PMOS device, is still operating in saturation. But once this output rises to 90%, by then it has switched to triode region. Then you use the triode formula and you get another current. Then you take the average of the two currents, plug it into the formula for time, and you get the time as 0.24 nanoseconds. You can see that, right? Then for part B, which is, same thing, you have to use that time formula for TPHL, which is again capacitance multiplied by some voltage divided by some average current. And he shows you how to do the average current calculation. That's where it's complicated always. First, you have to find the average current flowing backwards through this QE. First, when it's fully charged, right? When it's at VDD. So that is when it's in saturation. Then, when the voltage is dropped to half of the output VDD, then the N-type device, the NMOS device, switches into the triode region, so you use the triode formula. So you find the two currents, one in saturation, one in triode, you take the average of the two, you put that average value in the denominator of that formula for time, and then you get the final answer as 0.25 nanoseconds for TPHL. Okay. So with that description, I hope you'll be able to understand the logic. I think you'll understand a lot about how this dynamic logic gate works, all the switching between triode and saturation, when QP operates, when QE operates. So hopefully it's a good learning exercise. All right, I've got, I think, maybe just one more problem, the last problem, and then we'll be done. 1427. Here again, we are doing some logic gate stuff. Based on the basic dynamic logic circuit shown here we are told that this is the circuit for Y is equals complement of A plus BC. Now find NOT gate, NAND gate, NOR gate using the same dynamic MOS logic, also slightly more complicated, Y equals AB plus CD. Okay, so how do you do this? It's not difficult. Yeah, here's the answer. So how do you do a NOT gate? So A, you want it a NOT A, right? So this is how the circuit is connected. Here there's no analysis, no finding TP, HL and all that, just drawing these basic gate drawings. So here if you want to do a N AND or NAND, A and B are the inputs, you need a QP on the top, you need a QE on the bottom, you don't need anything else, and you get this Y equals AB. Here is a NOR, the two inputs are connected in an OR fashion, a parallel fashion, and the two additional transistors, one the P type and one the N type at the bottom. Now this is actually an N type, but we write it as QE for some reason. Then we have this slightly more complicated AB plus CD. So AB is an AND path, CD is another AND path, and the two are in an OR path. So that's why they are in parallel. And then the output is this. So here you can see, you needed 4 transistors here. In normal static switching, you would need another 4 for a total of 8. But now you have 4 here, 5, 6. You're able to get away with just 6 transistors instead of 8. So great savings, right, in area, in silicon. Okay, that's it. With this, we conclude chapter 14. In my next recording, I will look at a little bit of memory. Basically, we are looking at flip-flops. We are not doing too much memory, and I hope to finish that in one day's lecture, one theory and one problems. And with that, we'll be done with week 3 material. Okay? All right.